This is the most significant development we have encountered since the object was first identified on the approach. Today is January 26, 2026. We are broadcasting this update urgently because new high-resolution data from the Hubble Space Telescope has just been released, and it completely alters the scientific discourse surrounding 3I Atlas. We represent a community of inquiry that prioritizes hard empirical data over convenient speculation. What we are examining on the monitors this morning is a geometry so precise, so mathematically rigid, that it stretches the boundaries of standard cometary physics. If you are new to this investigation, I strongly recommend you subscribe to the channel immediately. The data stream is accelerating, the observations are becoming more critical, and we are analyzing every pixel in real time as it downloads from the orbital observatories. Let us look closer at the data, specifically the set of images acquired just last week on January 14, 2026. To the untrained eye, the raw frames from Hubble show the familiar fuzzy coma, that bright halo of scattering dust and gas we have been tracking since the perihelion passage. It looks like a standard celestial fuzzball. But the real story, the structural integrity of the object, is hidden within that glare. To reveal it, astronomers have applied a specialized image processing technique known as the Larsonina rotational gradient filter. This methodology is central to a groundbreaking new paper by Tony Scarmato, which was published online earlier today. For those unfamiliar with the algorithm, the Larsonina filter creates a processed image by taking the original frame, rotating it by a specific angle, and subtracting it from the original. This effectively cancels out any features that are perfectly circularly symmetric, like the glowing halo of the coma. Think of it as peeling away the bright, blinding outer layers of an onion to reveal the sharp defining structures of the core. When this filter was applied to the January 14th data, the nebulous glow disappeared, and what remained was shocking in its clarity. It was not the chaotic, turbulent noise of a sublimating ice ball. It was a perfect, symmetric triad. Let us look closer at the data, specifically the set of images acquired just last week on January 14, 2026. To the untrained eye, the raw frames from Hubble show the familiar fuzzy coma, that bright halo of scattering dust and gas we have been tracking since the perihelion passage. It looks like a standard celestial fuzzball. But the real story, the structural integrity of the object, is hidden within that glare. To reveal it, astronomers have applied a specialized image processing technique known as the Larsonina rotational gradient filter. This methodology is central to a groundbreaking new paper by Tony Scarmato, which was published online earlier today. Now, in science, skepticism is a necessary tool. A reasonable observer might ask, could this be a transient feature? Could it be a one-time outburst, a random fracture on the surface that just happened to vent in a symmetric pattern on January 14th? That is where the historical analysis in the new paper becomes the crucial detail. The research team did not stop at one image. They went back into the archive. They applied the same Larsonina rotational gradient filter to 24 other high-quality images taken by the Hubble Space Telescope over the last 2 months. We are talking about a comprehensive dataset covering observations from November 30th, December 4th, December 12th, December 27th, 2025, and January 7th, 2026. In every single one of those epochs across nearly 60 days of observation, this rotating system of 3 mini-jets appears. It is not a glitch. It is not a temporary flare. It is persistent, it is stable, and remarkably, it maintains that 120-degree separation consistently. The picture becomes even more complex when we analyze the full morphology. In addition to these 3 symmetric mini-jets, the processing reveals a 4th structural element. There is an anti-tail jet extending in the sunward direction. This 4th jet is morphologically distinct from the triad. It extends 10 times farther into space than the 3 mini-jets. This provides us with a very specific configuration. A system of 3 symmetric short-range jets spaced perfectly around the object and 1 massive long-range jet projecting out the back. So, what does this actually mean for our understanding of the object? In standard cometary physics, jets are formed by the sublimation of volatiles. You have pockets of frozen water, carbon monoxide, or carbon dioxide on the surface. When sunlight hits them, they turn to gas and rush out into the vacuum, carrying dust with them. For a rotating body, you would expect these jets to turn on and off as the active regions move into and out of sunlight. Or if the rotation is fast, you might see a lawn sprinkler effect creating spiral arms. What we are seeing here is different. It looks remarkably structural. The sheer persistence of that 120-degree angle over nearly 2 months implies a stability in the underlying source regions that is incredibly rare for a natural object undergoing the intense thermal stress of a perihelion passage. If these were random cracks in an icy crust, we would expect them to widen, to shift, or for new vents to open up and disrupt the symmetry. We would expect terrestrial-style chaos. Instead, we see order. We must also consider the viewing geometry. The images we are seeing are two-dimensional projections of a three-dimensional object onto the plane of the sky. The fact that they appear separated by a 120-degree in projection tells us something very specific and very constraining about the orientation of the object. If the jets were randomly distributed in three-dimensional space, identifying such a perfect symmetry repeatedly over weeks from changing viewing angles as Earth and the object move around the Sun would be statistically impossible. This suggests that the symmetry is intrinsic to the object itself. It suggests that jets are arranged in a specific pattern on the surface, likely a cone or a plane perpendicular to the rotation axis. The implications of this specific geometry, 3 points defining a plane separated equally, are profound when we start thinking about the dynamics of 3I Atlas. This is not just about aesthetic beauty or pretty pictures from space. It is about the physics of rotation, the tensor of inertia, and the distribution of angular momentum. The stability of this structure suggests that whatever is causing these jets is locked into the body of the object in a very robust, perhaps rigid way. This connects directly to the rotational behavior we have been tracking. These jets are not static features painted on a canvas. They are part of a dynamic moving system. And when we analyze how they move over time, the mystery deepens even further. We are seeing a wobble. We are seeing a systematic oscillation that hints at the distribution of mass within the nucleus. This is where the static image turns into a dynamic movie and the plot complicates significantly. We need to understand not just the shape of these jets, but how they are driving the object's motion through the void. This leads us directly into the new analysis on the rotation period and the strange precession we are currently observing. Let us transition now to the dynamics of this system because the static images are only half the story. The way this triad spins tells us even more than the shape itself. As we established in the previous segment, we have a geometrically stable triad of jets, but they are not sitting still in space. This brings us to the second major finding from the Scarmato paper released today, which concerns the time domain analysis. The team conducted a rigorous time series study of these images and produced a movie of the motion. The results define the heartbeat of 3I Atlas with a precision we have not had until now. The entire jet structure is wobbling. Specifically, it oscillates periodically by an angle of plus or minus 20 degrees. This is not a chaotic tumble, nor is it a simple rotation on a fixed axis. It is a rhythmic, predictable shift that repeats over a specific period. That period is 7.1 hours. To visualize this, I want you to imagine a lighthouse on a rocky coast. If the beam of the lighthouse is strictly perpendicular to its rotation axis, like a spoke on a wheel, it sweeps a flat line across the horizon. But if that beam is tilted, if the lamp is misaligned even slightly, it traces a cone in the sky. It wobbles up and down relative to the observer as it spins. This is exactly the behavior we are seeing with each of these 3 mini-jets. Each one is behaving like a misaligned beam from a rotating lighthouse sweeping through a conical volume of space as the main body rotates. This 7.1-hour period is the fundamental clock of the object. It tells us the rotation rate of the physical nucleus itself, but the wobble tells us about the orientation of that rotation relative to its orbit. The analysis suggests that the rotation axis is oriented surprisingly close to the sunward direction. We are talking about an alignment within 10 to 20 degrees of the sun. This is a critical detail, and it connects back to earlier findings in a way that is deeply satisfying for those of us who have been following the data models. Longtime followers of this story will remember that we inferred this exact orientation back in August 2025. At that time, it was a hypothesis based purely on light curve data, the way the brightness of the object flickered. Now, months later, we are seeing it confirmed in the physical movement of the matter being ejected from the surface. The consistency between the mathematical model from August and the direct imaging from January is striking. It serves as a powerful validation of our understanding of the object's kinematics. But why does this matter? Why does a 7-hour rotation significant? The answer lies in the forces involved. A 7-hour rotation for an object of this estimated size generates a significant centrifugal force at the equator. If 3I Atlas is a rubble pile, a loose collection of rocks held together by weak gravity, which is the standard model for many comets, that spin rate combined with this specific jet activity tests the limits of its structural integrity. This wobble also complicates the trajectory analysis. We have to remember that jets are not just visual features, they are thrusters. Every kilogram of gas and dust ejected at hundreds of meters per second exerts an equal and opposite force back on the nucleus. This is Newton's third law in action. If you have 3 jets firing in a discrete symmetric pattern and that pattern is wobbling by 20 degrees, you are introducing a complex time-varying torque into the system. This creates a feedback loop where the rotation drives the jet direction and the jets perturb the rotation. The fact that this system has remained stable for months despite these complex torques is the real anomaly here. In a typical scenario, torques of this magnitude would cause the rotation mechanism to evolve rapidly. We might expect the object to spin up until it flies apart or to spin down and enter a chaotic tumble. Yet here we are seeing the same 7.1-hour beat, the same 120-degree symmetry week after week. It implies a damping mechanism or an active control system that maintains the spin state against the perturbations. It forces us to ask a difficult question about the mechanism itself. Is this a natural venting process randomly stabilized by some internal friction or mass distribution we do not yet understand, or are we looking at something else? The precision of the 3+1 configuration, 3 symmetric mini-jets, and 1 major anti-tail jet begins to look less like a geological accident and more like a functional design. When we look at the physics of how to move a rigid body in space, symmetry is helpful. It allows for balanced forces. It prevents unwanted tumbling. The lighthouse wobble might not be an instability. It might be the signature of a specific type of maneuver or a specific type of stabilization known as spin stabilization, which we use in our own satellites. This leads us directly into the most speculative yet scientifically grounded part of the discussion. If we strip away our assumptions about icy surfaces and sublimating gases and look at this strictly as a mechanical system, what does it resemble? We need to talk about propulsion engineering. We need to compare what we see on 3I Atlas with what we build here on Earth. Because when experts in astrodynamics look at this 120-degree separation, they do not just see vents, they see thrusters. And that brings us to a fascinating question posed by one of my colleagues. Building on this idea of mechanical systems, we must consider the input of Dr. Frank Larson. He has reviewed the new data extensively, and his analysis bridges the gap between cometary science and aerospace engineering. He made a comment that strikes at the heart of the mystery we are facing. He noted, quote, "The symmetric 120-degree angular spacing between the 3 mini-jets is astounding. It is hard to imagine such a symmetry in a natural macroscopic object." I want you to take a moment to let that sink in. Nature is indeed chaotic. While we see beautiful symmetry in crystals or snowflakes at the microscopic level, ordered by the laws of atomic bonding, macroscopic symmetry in geology is virtually unheard of. We do not see three volcanoes perfectly spaced around the equator of a planet. We do not see geysers on Enceladus erupting in perfect equilateral triangles. Probability argues against it. Larson went on to ask the key question: are three symmetric mini-jets the minimum viable configuration of propulsion devices to reorient an object in three-dimensional space? This is where our analysis shifts from astronomy to engineering. If you look at human-made satellites, our thruster systems, what we call reaction control systems, usually come in pairs. We typically place them in opposing directions to cancel out unwanted forces. If you want to turn left without moving forward, you fire a thruster on the right, causing rotation, and an opposing one to stop the drift. For a fully orthogonal thruster system where you want complete control over every axis, pitch, yaw, and roll, and translation in X, Y, and Z, you would classically need 6 thrusters, 2 opposing thrusters, along each of the 3 orthogonal spatial directions. That is the standard textbook answer for spacecraft design. But spaceflight constitutes a constant battle against mass. Every gram counts. So engineers are always looking for the most efficient solution, the minimum viable product. Larson speculates that if 3I Atlas rotates around its major axis every 7.1 hours or so, then thrusters pointing in the direction of that major axis would not be very useful. The rotation itself provides gyroscopic stability along that line. Much like a spinning bullet or a football is stable in flight, so perhaps you do not need 6. Perhaps strangely enough, just 3 plus 1 equals 4. 4 thrusters in the plane orthogonal to the major rotation axis might be sufficient for some sort of technical manipulation, like attitude adjustments. And indeed, what do we observe? We observe a system of precisely 3 symmetric mini-jets plus 1 major jet. We are seeing the exact number of nodes required for a minimal efficiency solution to the problem of navigation in a vacuum. This is a provocative thought. It requires us to look at the anti-tail jet not just as a tail, but as a primary thruster, providing the delta V or change in velocity, while the 3 mini-jets act as stabilizers or steering mechanisms providing the attitude control. The lighthouse wobble we discussed earlier would then be the physical result of these steering impulses acting on the rotating body precessing the gyros. Now I want to pause here. This is the part of the scientific process where your input matters. I am curious what you think about Larson's engineering comparison. Does this 3 plus 1 configuration sound like a coincidence of ice and rock, a roll of the cosmic dice, or does it resemble a functional design to you? Leave a comment below with your thoughts on the efficiency of this geometry. Are we seeing a machine optimizing its fuel use? However, we must remain grounded in the data. Speculation is the engine of discovery, but evidence is the fuel. Additional data might help to address Frank's question. We cannot simply look at a shape and declare it artificial. We need to see it do something that natural objects cannot do. We need to see the geometry evolve in a way that reveals its three-dimensional nature without ambiguity. We need a test, and as it happens, the universe is about to grant us that opportunity. We are currently moving into a new observational window that will allow us to test these geometric hypotheses rigorously. In a paper by Marco Barbieri published just last week, the orbital parameters for the coming days were calculated, and the numbers tell us that we are about to see 3I Atlas from an angle that is nearly impossible to achieve with typical comets. We are approaching an alignment so precise it happens only once in this entire encounter. It is an event that will strip away the ambiguity of projection and show us the truth. This connects us directly to the immediate future, to an event happening in less than 24 hours. We are standing on the precipice of a critical observation window. In the paper by Marco Barbieri, which has guided our observing strategy for weeks, January 27, 2026 was identified as a date of singular importance. That is tomorrow. On this specific date, the observing direction of 3I Atlas from Earth will align to within 0.69 degree with the anti-sun direction. To understand why this matters, imagine you are looking at a flashlight in a dark room. Usually we see the beam from the side, we see the profile, the length of the shaft of light, but for a brief moment tomorrow, we are going to look almost directly down the barrel of the light. This is an incredibly rare alignment. 0.69 degree is a vanishingly small angle in astronomical terms. It is essentially a straight line drawn from the sun to the Earth to the object. When this happens, we get a unique perspective on the three-dimensional structure of the coma and the jets that is otherwise impossible to obtain. During this rare alignment, the projection effects that usually distort our view will vanish. Most of the time, when we look at a comet, we are seeing a flattened image. A circular jet might look like an oval, a spiral might look like a line. But tomorrow, if the hypothesis about the rotation axis pointing sunward is correct, and if the alignment holds, the rotating configuration of three mini-jets might trace a perfect circle in the sky. Instead of seeing flattened ellipses or distorted wobbles, we should see the true face of the system. We should see the clock face of 3i Atlas. If we see that circle, it will confirm the axis orientation with extremely high precision. It will also allow us to measure the spacing of the jets without the need for complex unprojection algorithms. We will see the machine if it is a machine structurally naked against the background stars. It acts as a geometric truth serum. This period is also known as the opposition surge window or the Seeliger effect. When you look at a rough surface with the sun directly behind you, shadows disappear. Every pebble, every grain of dust hides its own shadow. The result is that the object typically brightens significantly, a nonlinear spike in luminosity. We expect a spike in brightness data in the next 24 to 48 hours that could be dramatic. This surge will give us better signal-to-noise ratios than we have had since discovery. It means the faint structures, the edges of the jets, the subtle boundaries between the streamers will be clearer than ever before. If there are smaller secondary features hidden within that 120-degree spacing, features too faint to be seen in the side-scattered light of the past month, this is the moment we will find them. We are urging amateur and professional observers alike to train their instruments on 3i Atlas right now. The data collected over the next few days will likely be the most definitive of the entire passage. We are looking for that circle. We are looking for the ring of fire created by those rotating thrusters. Every telescope that can track it should be tracking it. However, we must prepare ourselves for any result. Science is about being open to being wrong. If we do not see the circle, if the symmetry breaks down when viewed from this angle, that too is data. It would force us to revise our models of the rotation axis. But given the consistency of the last 2 months, confidence is high. The geometry has held up since November. There is no reason to expect it to collapse. Now, this potential confirmation of the symmetric ring adds weight to the mounting pile of evidence that this object is unlike anything we have seen before. It is not just one odd feature. It is a compounding series of strange characteristics. When you zoom out and look at the full list of behaviors we have cataloged, the nature versus technology debate moves from a niche speculation to a necessary statistical analysis. We need to place this symmetry in its proper context. It is not an isolated curiosity. It is part of a much larger, more perplexing pattern that has been emerging for months. Given what we now understand about the symmetry and the dynamics, the triad, the wobble, the potential engineering efficiency, we have to look at the scoreboard. The symmetric jet structure we have discussed today is just one out of 18 distinct anomalies exhibited by 3i Atlas. Think about that number 18. We are not talking about 1 or 2 oddities. We are talking about the extreme non-gravitational acceleration that defies standard outgassing models. We are talking about the complete lack of carbon-based molecules in the spectra despite the object behaving like a comet. We are talking about the unexpected strength of the material which has survived intense gravitational tides without fragmenting. Any single one of these, The rotation rate, the spectral purity, the excess acceleration, the precise 120-degree jets could perhaps be explained away by a rare combination of natural circumstances. You could argue, well, it is a weird rock, but 18, the probability of 18 separate statistical outliers occurring in a single object by chance is astronomically low. It is like rolling a six-sided die 18 times and getting a 6 every single time. At some point, you have to verify if the die is loaded. This brings us to the Loeb classification scale. This is the framework we have formulated to assess the likelihood of technological origin for interstellar objects. It is a tool to quantify our ignorance and our discoveries. Identifying just one of these anomalies as a clear, indisputable technological signature would boost the rank of 3I Atlas high on the scale. The symmetry of the jets is currently the strongest candidate for that smoking gun. If it holds up, it pushes us past the unknown category and squarely into the likely artificial domain. If the observations from the January 27th alignment confirm the specific engineering constraints of a 3+1 thruster system, we are moving past the realm of intriguing space rock and into the territory of active technosignatures. We are building a case piece by piece, peer-reviewed paper by peer-reviewed paper. This is not science fiction, this is science in action. But scientific work requires patience. We cannot force the data to say what we want it to say. The universe does not care about our deadlines or our desire for aliens. New knowledge comes one day at a time. It accumulates. We have to be willing to sit with the mystery to let the observations guide us rather than rushing to a comfortable conclusion. We must be rigorous. We must be skeptical. But we must also be brave enough to follow the evidence where it leads, even if it leads to a conclusion that shakes the foundations of our worldview. There is a certain poetry to this process. Life brings joy when each day teaches us something new. I was thinking about this just this morning. My morning jog at sunrise was decorated by symmetric, fresh snowflakes falling around me. It was a reminder that nature loves symmetry too. But there is a difference. The six-fold symmetry of a snowflake is dictated by the lattice structure of water ice. It is a result of electrostatics and thermodynamics. It is beautiful, but it is passive. It grows that way. The functional 3+1 dynamic symmetry of a macroscopic object moving through the void is different. It implies intent. It implies agency. It implies a plan. There is nothing more invigorating than the beauty of symmetry in nature, both on Earth and in the sky. Whether 3I Atlas turns out to be a spectacular 1 in a billion natural comet or something sent by another civilization, the quest to understand it enriches us. It forces us to look up. It forces us to question our assumptions. It forces us to realize that we may not be the only ones playing the game. We will be covering the results of the alignment window as soon as the data comes down. We will analyze the light curves, we will process the images, and we will share the raw truth with you. If you want to be part of this journey of discovery, please like this video. It helps these updates reach more people who care about science. And if you haven't already, subscribe so you don't miss the breakdown of the January 27th data. The universe is speaking to us. We just need to learn how to listen.